So let's take a look at how fiber optics operate. And you may know a little bit about this. You've probably heard about it. Fiber optics work by total internal reflection. Let's talk about that for just a moment. Let's say I have a pond and there's water here and there's air above, and I'm going to shine a flashlight from the water, which has a higher index of refraction. The index of refraction is basically the speed that light travels through that medium. So the denser the medium, the slower light travels and the higher the index of refraction. So the water has a high index of refraction, the air has a low index of refraction, and when we are going from a high index of refraction to a low index of refraction, we get a phenomenon called total internal reflection. So let's get these letters out of the way here. And I'm going to shine a flashlight out of the pond, and there's going to be refraction. We've talked about that a little bit. So as the light goes out, it's going to bend a little, and some of it's going to reflect back. So we get some reflection and some refraction as we go from that higher index of refraction to the lower index of refraction. And the lower the angle, let's see if I can get a lower angle here. We're going to get more refraction. And reflection will have the properties we already know about. That reflection is going to be equal on both sides of the vertical line here. But when we're going from a higher index of refraction to a lower index of refraction, there's a phenomenon where we reach what's called a critical angle, where, let's do this over here. Let's say our light is coming in at this angle. There's our flashlight. 100% of our light is going to be reflected back and nothing escapes. So that is what's called total internal reflection. And it happens when we reach a certain critical angle, which depends on the materials involved. So if we can make a tube of glass such as this. There's the ends, and I shine a light beam in there. If the light beam enters at a high enough angle, a lot of it's going to escape. But if the angle is low enough, 100% of that will just simply reflect back and forth, and it can go down this great distances. And also, if we go around corners, as long as this radius is below a certain radius, that light will continue to reflect inside that. And there was a famous experiment about a little over 100 years ago by a man named Tyndall. Can't think of his first name, but there it is. He took an apparatus where he took a container of water, put a hole in it so there's water flowing out, and he shined a light in there somehow. Maybe he had a little window here or something, and the candle, I don't know, it's before incandescent lights. But he got a light beam going in there, and it followed that water and splashed out. You can look on YouTube and you can see a number of videos of people repeating this experiment. And so that is one of the earliest experiments that showed the principle of fiber optics and total internal reflection, was how that light beam followed that curved path of the water coming out of that vessel. So that is the classic definition of how fiber optics work. That's total internal reflection. However, modern fiber optics rarely use that. If you have plastic fiber such as the SPDIF cable in your audio system, if those are even used anymore, that's probably going to use that principle. We just have a fiber of plastic, and it can guide the light through a path from one component to the other. But other than that, there's not much application for fiber optics that use total internal reflection. So let's take a look at the other ways that light propagates through a fiber optic cable. First of all, let's take a look at the construction of a modern fiber optic cable. We're going to start with 2 layers of glass. Now, we don't need the 2 layers. I'm just going to start out with 1 layer of glass like we did before, and we're going to get our total internal reflection. I'll stop there. But there's a problem with that. What if you touch it and get a fingerprint on it? That's going to change the properties at that point there, and some of the light's going to scatter out, or it can get damaged, or all kinds of things can happen to that. So it's not very well controlled if we just simply have a single glass fiber. So what we do with modern fiber optics is we have two layers. We have a core which has a higher index of refraction than the outer layer, which is called the cladding. So there's the core, and then the cladding. And they say that the purpose of the cladding is to keep the light confined in the core. Well, it does, but that's not the purpose, because we don't need that cladding. The air can act as cladding. So we have the cladding there really to protect the core and to control the properties. So we have a higher index of refraction and a lower index of refraction, and the cladding protects the core so that we have controlled propagation. But there's a problem. The problem is that some of this light, let's get rid of our words here. Let's say we have one beam of light coming in at this angle, and it's within the critical angle, so we get our total internal reflection, and there's our path of light going down the core of the fiber optic. But now let's say we have another one coming in at this angle. Do you see the problem here? The one coming in at the higher angle has a longer path to go down the fiber than the one coming in at a shallower angle. And so we have a problem here. Let's say we send a pulse of light through, and what we want on the other end is the identical pulse coming out. But I like to relate this to perhaps a car race, whether it's NASCAR, F1, Indy cars, or whatever. Let's say, for example, we start out with a 30-car pack of cars, or a platoon, as a traffic engineer would call it. And they're going around the track, and we can see there's our platoon of cars. So let's just draw a few dots here. And there's the start, there's the end. They go by, we know where that platoon of cars is. So there's our pulse coming in. But as the race goes on, some cars are going to pull ahead, some cars are going to fall behind, and that platoon is going to get kind of stretched out. So instead of getting to, here's the cars, there's the cars, or not, now we get sort of a, well, there's some cars, there's most cars, and then there's some stragglers in the back. So we get a little bit of a lessening of that pulse there. But we can still pick that out. But what happens as the race continues to go on? So here's our racetrack. We'll just make it a simple oval here. And eventually we have the cars simply scattered all along that track. Where does the platoon start and where does it end? Some cars have even lapped other cars, so they're overlapping now. You can't tell where one begins and the other one ends, and so we just don't have a signal anymore if we relate that to the rays of light coming through the channel. So we need to mitigate that. And one way to mitigate it is to simply make the core smaller. So let's make the core a little smaller. Small core, keep our cladding the same size. And so we don't have as many paths. And by the way, those paths are called modes. So we call this fiber where we can have these multiple paths in there, multi-mode fiber. And so with the smaller core, there's not as much difference in what those modes are, what those paths are, so we mitigate somewhat. So let's make that core diameter something like maybe 8 times the wavelength of the light. And wavelength is something we didn't talk about in AC because it's not relevant, but it is to communications. The wavelength is going to be the distance between the electromagnetic pulses as they travel through. It's basically the speed of light divided by the frequency, but we're not going to get into that. But anyway, 1,000 nanometers. So at 1,000 nanometers, that's 0.000001 meters, or 1 micron, 1 micrometer. Now let's make this core 0.000008 meters, or 8 microns. So our core is 8 microns in diameter, about 8 times the wavelength of light. And we get a whole new phenomenon when this happens. Now, what happens is that the energy begins to travel down the fiber as an interaction between the core cladding interface. And we do not have any more of these reflection modes or these paths down the fiber. We have simply one. This is called waveguide mode propagation. And so there's only one mode, or one possible path. So we no longer have the problem that we had with multi-mode fiber, where we have some light taking a long path, some light taking a shorter path, and we get modal dispersion, as it's called, because of the multimode fiber. So that's one way to mitigate the modal dispersion, is to use what's called single mode fiber, which once again we have a very tiny core, so that the light energy follows along the core cladding interface, and that's why we call it a waveguide. It works just like a radio waveguide, which we'll talk about down the road in communications. But there's yet another way to mitigate it, which is a compromise between the two. So I'm going to start out with a chunk of glass. Let's make a glass tube of 1 index of refraction. But what I'm going to do is now put that in a chamber, and I'm going to put in some gases in there. I think they're germanium tetrafluoride and silicon tetrafluoride gases, and they're going to go in here and they're going to deposit a soot on the side. And then I'm going to heat it up and I'm going to melt that soot, and it becomes pure germanium oxide and silicon oxide of the right proportion. But I'm going to have that first set of gases give me a little higher index of refraction. And I'm going to do that again and again so that my index of refraction starts out low and gets higher and higher. I don't know how to illustrate this, but low index of refraction, higher, 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 and of course in the middle it's the highest index of refraction. As I go to the outside, I get lower index of refraction. And then I heat it up and collapse it to make sure there's no air in there. And then I stretch this out for who knows how long, and I now have a fiber optic where the core has a higher index of refraction in the middle and a lower index of refraction around the edge. So what's that going to do? Here in Southern California, we have a phenomenon in this time of year. It's December, usually starts around late August or September and goes on into almost January. And we call this Santa Ana winds. What we get is a high pressure area over the Great Basin area, and that causes a clockwise circulation in the winds. And us down here in Southern California get these easterly or northerly winds coming down. And living near the coast like I do, they come down the coastal range and the transverse range of mountains. And as that air comes down, it heats up. Now, in the early fall, we get our hottest and driest days of the year during the Santa Anas, but as the year goes on, it gets into winter, they can be actually pretty cold. But they're warmer than the air in the valleys. So what we get is a layer of cold air in the valleys. So here's our mountains, and here's the coastal valleys, in which I am in one. And we get these layers of cold air with this katabatic air coming downslope, being warmed up a little warmer above it. So we have the cold air and the warmer air. And I can walk outside and I can tell you, we're having a Santa Ana today, because not only is it crystal clear skies, but I can hear the cars on the freeway a couple of miles away, and I don't normally hear them. Why is that? Because out here on the freeway, all the cars and trucks and everything are going back and forth, and the sound is going like that. And not very much of it reaches me. Normally, it just dissipates. But when I have that warmer air on top, this sound on top, I'm going to use my pin as an indicator. Remember what happens, it's going to speed up in the warmer air. And so this is going faster than that. And so it hits that warmer air, and it is going to pivot right back down. So that sound comes right back down, and so I can hear those cars in the freeway a little bit away. Now, I had a friend ask me once who lived up on a hill. He said, it's really funny. When we're not having a Santa Ana, I can hear the cars in the freeway, but when we are having a Santa Ana, I can't hear them. Just the opposite of what I get down in the valley here. And that is because, of course, normally the sound goes up and he hears it. But now the sound is being refracted back down and he doesn't hear it, so it gets just the opposite effect. What's this got to do with fiber optics? Highest index of refraction, lower index of refraction. So we go from a higher index of refraction to a lower index. We're going to get that bending effect where the sound is going to be curved back in. So graded index fiber optics use that same phenomenon with light. Let's draw that core out as a bigger size here. So let's send a light ray in. As it goes in, what's going to happen? As that light wave comes in, now Notice that this is a lower index of refraction here and a higher index of refraction there, so the light is going to travel faster on this side of the wave and slower on that side, so it's going to pivot. And it's going to go down like this, and it's going to pivot back again as it goes back and forth, and it never reaches the core cladding interface and just simply goes down in a serpentine path. So that actually confines the modes to a smaller area. So it's a lot like making a smaller core, but this keeps the waves near the center. And so this also mitigates the modal dispersion that we already talked about, and this is called graded index. So we have step index, which goes one index of refraction, lower index of refraction for the cladding in the core. Graded index means that the core has a high index of refraction in the middle, lower and lower and lower toward the edge, and then finally a cladding of much lower index of refraction to make sure that any light that does manage to hit the edge reflects back in. So that is called graded index fiber. That's probably the most common type of fiber you're going to encounter in a data center if you find yourself in there. Now when it comes to single mode fiber, you're more likely to find that outside plant going great distances. So your multi-mode fiber, which is either step index or graded index, modern fibers are all graded index. You're going to find in data centers, you're going to find that multi-mode fiber, and you'll notice that your cables are either orange or aqua in color. I'll talk about what that means later, but all your multi-mode fiber is going to be the orange or aqua depending on the type. And your single mode fiber is going to be yellow. So that's one way you can tell them apart is from the jacket color.